All right, good afternoon. You all here online there? Good afternoon. Yeah, you all here? All right, so we just want to wrap up this part of analog physics on the op amps. I'm just waiting on a few others. They're hoping to come. But last day, if you remember, we spent some time on the inverting op amp and a couple examples of one example of how we can apply the op amp, right? Here we have the two types of op amp, the inverting and non-inverting. I just know which is which again. Fires know which is the inverting and which is the non-inverting. Anybody remember? Right? So for the inverting op amp, you will see it here. For the inverting op amp, the non-inverting terminal goes to the earth. For the non-inverting, the inverting terminal goes to the earth. Or you could also say the input is run through the inverting terminal for the inverting op amp, or the input is run through the non-inverting terminal for the non-inverting op amp. All right, so those are your two types of op amps. We did a couple examples, right? And the last one we did was a summing amplifier. Or if I get disconnected again. Right, the last thing we did was a summing amplifier, right? Let's just spend some time on the non-inverting op amp. Right, look at the, well, there's one main application, and then we could take a look, and then we could do some past papers on wrap up, right? You might need graph paper today. Get disconnected that key. Hold on now, I keep being disconnected. Till the Wi-Fi starts up there. Yeah. All right, good. And not disconnecting so much again, right? All right, so here we have all these here we have all these different oh, it's going again. It's the last time I gotta write everything, right? Right? So as I said, here you have two different types of op amps, inverting and non-inverting. For each one, you have the gain, right? Take a look at the picture here. This picture has 4 op amps and tell me what type of op amp each is, right? Huh? Oh, I disconnected there too. In case you get cut off again, I'm gonna try to I'm just gonna try to I'll just probably pick any or just take it, right? Oh, I was sent on the group. I'm gonna send on the group first. Right, in the group, I sent a pic just in case I get disconnected again, right? All right, I'm gonna try to airdrop it here. All right, so before we do the last application of our pump, here we have 4 pumps. I sent in the group. Right, do me a favor, write down the type of each one, write down the type of pump and the gain for each one. Right, so state the type and then we'll find the gain for each one, right? Finish already? Finish all four? I've got before. Ready? Finish? All right, let's check it out. So first one here, what type of op amp is this? What type of again? Non-inverting. The input run through the non-inverting terminal. So it's a non-inverting and the gain is 1 plus. This is your feedback, right? But sorry, I drew the arrow the wrong way. That's the feedback. That's the input. So I got 7. Yeah, gain is 7. Nice. Next one. What type of op amp is this? Non again, right? Non-inverting again. So that's 1 plus. The feedback is 40 on 10. The good thing is the feedback always larger, right? So that's 4 on 1, 5. Nice. Type. What type is this? The inverting. The input is run through the inverting. The non-inverting connected to earth. Right? This is earth, right? So this last type here is inverting op amp. So that would be minus 250, which is minus 4. Right, look at the input and let's try to figure out the last one now. Minus 4, don't forget to have the minus sign. Last one there. What's the last one? Non-inverting again. So that would make it even. Non-inverting, so that's 1 plus 520. So that's 11. Yeah. Sorry, 2 to 25 is sharps. Sharps. 25 and 1 is 26. How about it? Yeah, why not? That's module 3. Yeah. In module 3. Okay, nice. So that is the. Wait, why disconnect? I disconnect. Oh. It wasn't showing all the time? Oh, it wasn't showing? Oh, I didn't try it back. Okay. Huh? Okay, so those are the different types of op amps, right? Non-inverting and the inverting. The next thing that we have to be able to do, last thing, is a specific type that you will see. It's called the voltage follower. And that's it. We can do some past papers after that. All right, I'll draw this one. So one of the applications of the non-inverting is something called a voltage follower. All right, let's see. If you do get connected, just join online now. Right? I'm gonna just try one more time. Yeah, log in now. It's not working. I just keep behind. Look at this thing drop again. All right, so forget that, right? So we're taking a look at the voltage follower. And here's how it looks. The voltage follower is a little bit different, right? Again, you have the input being run through the non-inverting terminal. But look at this. Look at our op-amp. It's a non-inverting for sure, right? But what's the difference here with this compared to all the others? It have no resistors, no feedback resistor, no input resistor. So if you had to guess, what would the gain be? Gain will be 1. Gain is 1. Right, so the gain is 1. Right, how they work it out is like this. RF on RI, the feedback resistor, right? The feedback resistor has no resistance. But what is the input resistance? Anybody remember? What is input resistance per op-amp? Input impedance per op-amp. Anybody remember online? What is input impedance or resistance for an op-amp? Check back on the properties of the op-amp. Correct, Sylvie. The answer is infinity. Right? And 0 and infinity is 0. So it means that the gain here is 1. So once you see this op-amp with no resistors, that op-amp is a voltage follower. And the gain is 1. Right? And the application, it is used as a buffer. Right? It's used as a buffer to hold a voltage and give you back the same voltage. Right? Because if the gain is 1, it means that Vn will be equal to Vout. So it's used as a buffer. All right, so that's the voltage follower. That's all you have to know, how it looks, what the gain is, and what it's used for. Right, let's try a small question on this and then we could look at some past papers. Actually, let's go into our past paper one time. Let's take a look at 2003 again. I did 2003 last year? 2000. Oh, I did 2003 paper 2 number 6. Right, so we'll go straight into the past papers one time. Right, what I'll do is I'll share it on the group for those who want to go faster because we're doing the whole thing. All right, let's start here. Right, do I to write it out? Just tell me what it is. Say the 3 characteristics of an ideal op-amp. What are the 3 characteristics of the ideal op-amp? Andy, you remember? Turn back now and just read it. Come on. What are the 3 characteristics of the ideal op-amp? The ideal. What are the 3 characteristics of the ideal op-amp? Remember infinite open loop gain? Remember infinite open loop gain? The first property of the op-amp. You didn't remember I give a picture of properties of the op-amp? Look at voila. I don't want to take off this one. I think I had put up a photo or something I don't think I'd call it out. You only remember that online, the properties of the op-amp? Very high open loop gain, high input impedance, low output impedance. All right, in case you didn't get it, I'm gonna send back a picture. I can't remember what's on a picture or what I did. I send it back in the group chat when you fall asleep. Probably didn't write it down. I think I sent a picture. Yes, I remember doing this bandwidth and thing. I remember the graph shape like what? Check in the group. See if you remember that. Hold on, then send us it. Check it and see. See. Yeah, you remember that now? Right. Oh, take a picture and we just read it through. Yeah. Right. So you see why you mustn't take a picture alone? Because you don't write it down and you don't know what's going on. You told us to because and leave a little space to write it down. All right, so the ideal op-amp, the infinite open loop gain, that's the first assumption. and they give you some of the implications underneath. And infinite input resistance, impedance and zero output. Right? So you don't have to write that over. Actually, I should make somebody write that over. Right, Andy, you should probably write that answer down.
Yeah.
What effect does negative feedback have on the gain? So if we go back to the graph on top, negative feedback does what to the gain? Anybody remember what I said? Negative feedback, does it increase the gain or decrease the gain? Decrease, yeah. So the negative feedback will reduce the gain and do what to the bandwidth? Larger or smaller? Larger. So it will drop the gain. Look at the graph. I think I have a kind of line on the graph there. The lower the gain, the larger the bandwidth. So since you all didn't write that down, just do me a favor now. Answer part 1 and 2. Actually, we'll write it down. Right? Answer part 1 and 2 there for the question. 8 marks. Then we'll go to the cascade cell. Well, yeah, this is 2003 paper 2 number 6. You have that, right? Right, so remember negative feedback will drop the gain and increase the bandwidth of the op-amp. The bandwidth is the operational frequencies, right? Right, when you finish, let's take a look at B. Bandwidth here, and just make a note what bandwidth is, the range of operational frequencies. band and width WID. Whatever outcome is the first one, and the next one, and the name I just say follow. Nice. Go ahead, do part 1, 2, and 3, and then we have last part there to do. Finish the whole thing. All right. This part two, right? Yeah. Beautiful. So let's take a look at this. Right, nice easy question. You'll see do have graph paper. Not even one page. All right. Let me see. Anybody working online still? All right, so first part here determine the output voltage. So we need to get a gain, the gain for the first part, that's A, right? There's an inverting op amp, so that's minus 150, which is minus 2. The gain for B is just 1. So you multiply them, and you'll get the overall gain. So the overall gain is minus 2. So to get V out is gain by V in. So that's negative 3 volts, right? Sorry, negative negative 2 by 3. So that's negative 6 volts. A practical use for B is a buffer, is a voltage follower. So a practical use is a buffer. The entire circuit in figure 6 saturated at plus or minus 13. What is the maximum input that will not cause saturation? So maximum Vn is the supply plus 15 over the gain. The gain was minus 2. So that'll be around what, 7.5 plus and minus. Well, the maximum is plus 7.5 volts. Wait, sorry. This says saturated at 13. Plus and minus 6.5. You got that? So they want the maximum input that will not cause saturation. So that maximum value is 6.5. And the other get how much you get? What I mean? 6. How you get 6? Huh? So where you divide? Oh, I mean like that. Oh, okay. Okay. So the largest value is 6.5. I don't understand what you're talking about. So you can use the formula. All right, nice. So that is your first part. Second part, sorry, third part is where they ask you to draw the circuit, right? Just like yesterday. This is a 3, 1, 2, 3. Right, between 10 and so you want to get minus 3 V1 minus V2 minus 5 V3. Right, between 200 and what? 10. Right, so you can use any value, right? I just using 150 here, 50 here, 150 here, 30. What you all use? Huh? Same value here. You can use any value you want. You can even put the decimal, like use 200 and get decimals and it don't matter. Right? Once your values work out to be the same things, right? So this is V1, V2, V3. Are you okay with this online, Shivani? Right, nice, Katrina. Right, let's go up the road. Let's do our next one. You all don't have graph paper, right? I'm gonna give you something a little more recent. Anybody have a soft copy of 2012? If we have a soft copy, we can kind of do the graph together. All right, let me see what I have a soft copy formula. Is normally have a graph page there, so we can do it together. All right, let's try this one here. This is a more recent year, 2011. Right. First part is we have to connect up the what's on is logic gates. We can leave out logic. That's what the analog part alone. Right? Explain what is bandwidth and feedback. What is bandwidth? What's bandwidth, Olia?
The rate of operational frequencies.
Nice. What's feedback? Feedback is when the output voltage, right, is run back to the input voltage. So basically the output is fed back into the input voltage. And what does feedback to do again? Well, right, negative feedback will drop the gain of the op amp.
Yeah.
Try part 2. What type of op amp looking like part 2 there? What type of op amp is that? Huh? No feedback. Once it's not seeing feedback, is not an invert, no non-inverted. Is that what? The? You have 2 inputs. What's it good? What's the next one? Comparator. That's the first one. Right? So you have an alternating input and your voltage connected to 0. So that's a comparator. So you got to go back to Saturday. You got to go back to Saturday. Yeah. Right. But anyway, let's do it back together in case you forgot. Anybody remember the way I solved this? Remember, I did we did it by a circuit. So we had an alternating peak to peak is, oh, what does peak to peak mean? I don't know if I remember that from Form 5. Peak to peak means a peak to peak voltage means from this peak to this peak, that voltage is 2 volts. So it also means that if the peak to peak is 2, the highest is 1 and the lowest is -1. Right? And it saturates at plus and minus 5, right? Anybody remember what to do? Let's say up here is 5, down here is -5. The red is the inverting terminal, and I will draw a black line for the Q, non-inverting. Anybody remember what to do? What you do here to figure out the output? Anybody online?
And then yeah.
So draw your lines where they intersect. Draw your lines where they intersect and then compare the regions, right? So the red is more than the black. Yeah.
Negative.
It will saturate low, very good. So it will saturate low because the inverting more than the non-inverting. And if the black higher than the red, it will saturate high. Then low, then high. Guys, catch that quick. Right? Now do the last part from up please. Here's what they did. They complicate it a little bit. Across the non-inverted now, instead of 0, they put a constant 5 volts. Sorry, 0.5 volts. Chance if we can explain what happened there. The best way to explain it is to do back the whole thing. So you see what I had here? Go back and do that. Move the black line up. The black line. The black line will be like, they said 0.5, right? So the black line is there. And in the middle. And check and see if your output identical to what you see in there. Your output's supposed to look like the one in black. Right, we still have something else to do in mod 2, eh? We still have one little thing to do called alternating circuits, right? No, we'll do that when school reopen. I'll probably do that and lead into electricity, probably. Right, so you all got it? It looks like the one to the left. So let's see, the black is higher than the red, so it will saturate high. The red is higher than the black, so it will saturate low. Here, saturate high, low, high. Right? I just joined the graph. That's a full explanation right there. All you have to do is, if you want, you could, and I would have done this as well to explain it properly. You could say in one, the non-inverting bigger than the inverting. Here, so it's saturate high and it got 5. In two, the inverting is more than the non-inverting, so it's saturate low. And then it continued after that. So just talk about this first gap here and the second gap. Okay, and then make sure you have a graph. Right? Once the graph is identical to this, you're good to move. All right. Let's go to our next one. Let's go to one that's more recent, right? So you will see how long the question is, right? I think I shared it in the group 2022. 2022, number 2. Remember, your paper is just 2 questions or 3 questions alone, right? 21, I mean, 21. Sorry. And? Yeah, 21. Don't think you need to draw a graph, right? Diagram, answer that. They give you a graph, good. And then you work out your conversions. Go ahead. Number 2, yeah. If you do this good, we can stop after this. Or else I'll give you our next one. All right, and that's the end of that part, analog and digital. We still have one more thing called AC theory. That's how to convert your rectification, I think. Half wave and remember half wave rectification, right? We had to learn half wave, full wave, and a little bit about transistors on that. Right, we'll do that first thing. Our class will be on a Friday evening, right? 5. 5,000. Yeah, I'll see you in an hour and a half. I want to increase. But the one that time or only later time, half 6, eight.
No, I'd rather.
Bye. Well,
School though,
just come power better. Because you had one, so I just put it up with. Somebody had to get it back. You just one again.
Yes, yeah, that, you know, like that, the hot one lines of trees, right, you have two of them, so we would get over that, and you know, put them on and get it. Right, so that's what I say, I have a more for like you. Hot one. Well, we just like that, because it's not very, and I like them. But if I, no, those smart ones, it's for you. The subject of any like.
But I have one more side of energy.
Yeah, that's all.
Oh, yeah, yeah, yeah. You do very, I'm not a good job. Sort of that feeling.
Yeah.
Yeah.
Yeah, it's taken out the office. Oh, you better help with the music. Operating that just count for you.
I got an option.
Well, we take it, That's Oh, when I see the say 110,
You were looking at those, I think, I think I would have said. Yeah, the fair no. Yeah, they didn't think they could more fun than something. I was there, you got a pizza, wasn't the first one I had. You know, am I very used to?
that's all right.
I think you know,
Yeah.
I remember the, tell me, who was something that.
Good morning, mother. I just drink coffee.
I didn't think really want to go and put myself see. I didn't like four. Like that one day.
Yeah.
Oh, I don't think I too.
Yeah.
I feel like that. I got take the lunch.
Yeah, I know.
Yeah, you got part of it.
I've done the whole question already.
We didn't do the graph parts, but the rest is stuff.
So fast, much man.
Breakfast done.
Yeah, breakfast. Bro, the breakfast.
At 2:07.
So far. We just make sure we do this, we all do the same.
Same question.
Everybody finish order. So number 1, A and B, easy. Derive a relationship for the input and the gain. And you take the graph. Y'all do all this too, part C, for the summon amplifier. Yeah, the whole number 2 you have to do. Oh, I want to know how to finish. Nah, the whole thing. Then I will correct it. Right, but part A, okay? The 3 major properties of an ideal op-amp. Right?
Yeah.
Yeah?
Infinite.
Right. Same.
Impedance and zero.
Right. Draw a diagram of a non-inverting. I can handle that. Right. Use a diagram B part 1 to get a relationship between
You just get 10, so 110. I mean,
derived between input and output for non-inverting. Oh wait, what should I do there? That's not right. So we label everything. Labeling an input and all the voltages, right? Derive a relationship. Right, we know that gain is equal to V out and V in. Sorry, that's not right. And gain is equal to 1 plus unless they want us to go backwards, relation between the input and the output. Right, this is the only thing I could think about that they want, right? I by Ri plus Rf all over I Ri. That'll be voltage output on top over voltage input. Right? I'm not sure why they're asking us to derive it from here, but
No.
right. So this here would have been your circuit for the this here would have been your circuit for the VM. Right, so V out to get it V out, you might see it here in the circuit. V out is you connect it here across the earth. That'll be a V out. Right, that'll be a V out there. That's how come I got I by I. These two in series. So I got I by Ri plus Ri. Right, and the input impedance, you can connect it here to here, you'll get your input. That'll be the same value as here. Right, because remember, input impedance is infinity.
We didn't have to do that, just I should do it.
Yeah, so I think they want you to show this. This diagram is what you would have had initially, part one. All right, so this is the only thing I think that I could have gotten there. So you're kind of proving the reverse. We already know it, but you had to prove it.
But no,
All right, make a note of that. So a non-inverting operational amplifier has a gain of 11. Suggest practical values that you can use in your circuit. 10 and oh, 110 for RF and RI is 10. 10, yeah, that could. Oh, wait, no, all right. Remember the formula was 1 plus. So it should have been 100, right? And just make sure you're valuing kilo ohms. So it's 100 kilo ohms and Ri could have been 10 kilo ohms. Right? Remember the formula is 1 plus 100 over 10. That's okay? Are you okay there, Ronel? Raul? Karina, are you okay there? Rika? All right. So just finish it up there. They gave you the amplifiers powered by 10 plus or minus 10 volt, and it's fed with a triangular wave input. They show you the triangular wave input here. Time in milliseconds, and they give you the voltage up there. Sketch the output voltage. Sketch the output voltage, labeling the maximum and minimum points, right? So I will probably help you with that. Right, because I have the graph here, right? So you know you cannot go beyond plus 10 and minus 10, right? Those are the saturated values. And this is the input here. That's the input. So this is not a comparator, so you're not comparing anything. We have to figure out what will cause saturation. So we have to work out plus and minus maximum Vn, max and min Vn. So that'll be plus or minus supply over the gain. So that's plus or minus 10 over the gain was 11. And it was 11, right?
Yeah.
Right. How much is that? See your point? 10 divided by 11. So 0.91 volts,
Yeah.
right? But plus and minus.
And
So any value bigger than plus or minus 0.1 volts will cause saturation, right? What type of op amp is this? Inverting, non-inverting? No, what type of op amp it was? Non-inverting, not inverting. Right. So it means that the positive input will give you a positive output. So let's draw the line for plus and minus 0.91 now. So I see in 0.1. So that's 0.2, 0.4, 0.9 is like in the middle here somewhere, right? I just averaging, right? Somewhere here as well. So any value that goes outside of those lines will cause saturation. So this one will look like this. A little bit different, huh? Any value that and that peak there will cause saturation. But this is not a comparator. This is not a comparator. So you will have readings once it's below 0.91. So you will have a straight line looking like that. So your graph will look something like that. Right? So the shape like this, it went up, cut off it up, went back down, cut off it up. Sometimes this is called clipping, where you clip off this peak here. Okay, screenshot that now, please. All okay, what happened there?
yeah,
All the values above 0.91 cause saturation. So it's plus 10 and minus 10, but it's not a comparator. A comparator will only give you high or low, but other op amps will give you values in between. So there's a slight slope connecting it up. But you do it the same way that we did the other graphs. Do the saturation points and then connect it up. Right, so screenshot that there. Those who could draw it will draw it in. All right, last part. So they want you to calculate the value for the resistor such, oh wait, so sorry, I'll leave out a part. Try this here. So Andy, here's what we have. We have a summing amplifier that could convert a digital signal to analog. We had to figure out how to work. Figure 5 shows an op-amp, an operational summing inverter, which may be used to convert digital to analog. Sorry, the other way around. Digital to analog. So you're taking ones and zeros to give you an analog. Consider the case where digital 1 is represented by a 1 volt and 0 by 0 volts. Complete table 2. Complete table 2 for input-output characteristics of a 3-bit. What's all that? We're talking about it. What are they talking about? Right, remember it's digital to analog, right? Anybody recognize it? What they want inside it? Binary, yeah. So the 1 0 0 0. What will that give you? 0. Then the 1 0 0 1. What will that give you? 1 0 1 0. What will that give you? 2. Then the 1 0 1 1. What will that give you? Yeah, right. Not the screen. Yeah. Oh, that's for the previous writing. Yeah, I take it off.
Yeah.
Right? Well, I want to go so big because they're going to ask you what resistors will give you that, what values. Right, so we said 0 0 0 will give you 0. 0 0 1 will give you 1. Then you have to get 2 3 4 5 6 7. So 0 1 0 0 1 1 1 0 0 1 0 1, then and then, right? So that's how you fill the table out. But here what you need to go back and figure out what values for these resistors will give you that. See if we can figure that out. Remember, there's a general formula for it, right? Check back from last day and you will see the general formula for the summing amplifier.
Yeah.
That's the next part, right? The next part is calculate the values for the resistors. That'll give it. Remember the general form we did last day? Right, negative RF on R1 in this case. RF1, RF1, and that'll give you the V out, right? But you have to figure out what values will give you that. So remember 0, 0, 0 have to give you 0. 0, 0, 1 have to give you, and so on, right? Think about it. What's the first? What's the first column? The first column was what? Ones, twos, or fours? The first column, like for example, 1, 1, 0. And the first column was ones. Second column was twos. Third column was. So you had to figure out what will give you ones. This have to give you ones, this have to give you twos, this have to give you threes. Fours. So you had to get RF on R1 values, that'll give you ones. RF on R2 values, that'll give you twos. RF on R3 values, that'll give you the fours. They didn't give you a range, so you can do anything you want. But let's stick with the 200 to 10, right? Any answers online? What y'all think we could use here? Yeah, so what y'all decide? RF is what? Hundreds? There's 100 over 100. So by the way, I write in 100 over 100, but you write in RF is 100 kilo ohms, right? Next one is what? Over 50, nice. Kilo ohms, right? And last one. Nice. 100 over 25. Right? And you have it there. Right? That will give you 1V1 minus 2V2 minus 4V2. Right? That'll be a V out. That's a very comparator. All right, good. I think it had one more little part. What's a major disadvantage of a circuit in figure 5 from digital to analog? Kind of in the word, one of the disadvantages. What's the disadvantage? Oh, cover something else now. Just one disadvantage.
Fixed resistance.
Fixed resistance, no. Yeah, one disadvantage. Could it count more than 7? Could it count more than 7? No. So you had to keep adding on resistors to get more bits.
Right.
And also, would it be 100% efficient? No. It wouldn't be 100% efficient. So you wouldn't get exactly 1 or exactly 4. Right? Those are two disadvantages.